This video will show you how to make a moving phase boundary simulation using the graphical mode version of the Diffusion Module, also known as DICTRA. This example only uses two elements, so it can be run even if you do not have a license for the Diffusion Module using the free demo database packages included in your software. In this video, I will show you 3 ways to make a moving phase boundary simulation. All 3 examples use the same alloy, a steel with 0.15% carbon. All 3 examples simulate the growth of ferrite, BCC, into austenite, FCC. The first 2 examples are isothermal, and the third is non-isothermal. The calculation is based on Diffusion Module Example 2, which can now be accessed from within Thermo-Calc in the Help menu, Open Examples, Diffusion Module DICTRA. If you want to run the example as it is, double-click on the example file, then right-click on the top node, and select Perform Now. In this video, I'll walk you step by step through how to set up the calculation and explain what I'm doing. You can learn more about moving phase boundary simulations by going to our online help system. The files open in an internet browser, but they are stored locally on your computer, so you do not need an internet connection to access them. From the main menu, select Diffusion Module, Graphical Mode Quick Start Guide, Moving Phase Boundary Simulations. Here you can learn about the theory behind the simulations and more. For the first example, both phases are assumed to be initially homogeneous, and the transformation temperature is 1050 Kelvin. The initial thickness of the austenite is 2 millimeters, and an initially very thin ferrite, 1 nanometer, is also present at the start of the simulation. To begin the calculation, click on the Diffusion Module template from the home screen of Thermo-Calc. All the nodes we need to run a diffusion simulation will appear in the project pane. Highlight the system definer, then select the Demo, Steels and Fe Alloys database package. This will load both the thermodynamic and mobility databases. Select the elements iron and carbon. When you are making a diffusion simulation, you do not need to set the material composition, since the compositions in the diffusion module vary with distance. Next, select the Diffusion Calculator node, which opens the diffusion module. We will accept the default composition unit of mass %, but we will change the length unit to micrometers. We will accept the default planar geometry. Next, we will define the region. All diffusion simulations require at least one region to be defined. Our simulation has 2 regions, ferrite and austenite, so we need to add a second region. To do this, click the green plus sign next to region. A second tab appears, so we have a tab for each region. Double-click on the left tab and type ferrite, then press Enter. This changes the name of the region to ferrite to help us identify which region is which. You can change the order of regions at any time by right-clicking on the tab and selecting Move Right or Move Left. Click the ferrite tab. In the width field, enter 0.001 micrometers. Notice that when we entered a width, a visual representation of our region appeared in the form of a colored line, known as the domain. Change the number of points to 10. Notice that when we change the number of points, the dots on the domain change. We will keep the type as linear, which means that the grid type is equidistant, which is represented visually by the equally spaced dots. Next, we need to select our phase. There are several phases listed, so if you do not know which phase to select or their compositions, you can quickly calculate a phase diagram to determine this information. Right-click on the System Definer node, highlight Create New Successor, and select Equilibrium Calculator. Under Calculation Type, select Phase Diagram. Right-click on the Equilibrium Calculator, highlight Create New Successor, and select Plot Renderer. Then right-click on the Plot Renderer node and select Perform Now. Once the calculation is complete, an iron-carbon phase diagram will appear in the results pane. We are interested in the phases present at 1050 Kelvin for a steel with a carbon content of 0.15 mass %, so zoom in to get a better look at this region. At 1050 Kelvin, with a carbon mass % of 0.15, we can see that the only phases present are FCC and BCC. You can see the equilibrium information by hovering your mouse around 0.15 mass percent carbon and 1050 Kelvin, then right-clicking and selecting Add Label. Then Show Details. The carbon content of the BCC phase is about 1 to the negative 4 in mass fraction carbon, which is equal to 0.01 mass percent carbon. Close the dialog box and return to the diffusion calculator. Set the phase to BCC-A2, which is one of the two phases we saw in the phase diagram. Then click Edit next to Composition Profiles. We will leave iron as the dependent component and linear variation as the initial carbon profile. Enter 0.01 in both fields to represent carbon going from 0.01 mass percent on the lower left-hand side of the system to 0.01 mass percent on the upper right-hand side of the system, which we will see in the plot when we run the simulation. This is the mass percent we saw in the equilibrium calculation. Click Apply. We will now set the second region, so double-click on the second tab and name it austenite. Then press Enter. In the width field, enter 2000 micrometers. Notice that the domain turned entirely red. This is because the austenite region is so much larger than the ferrite region that the ferrite region is now too small to see. If I were to enter 0.001 in the austenite region, the two regions would be the same size, so you could see both colors. But in our simulation, austenite is 2000 micrometers, so I will change it back. We will leave the number of points as 50, but we will change the type to geometric and change the ratio to 1.05. Notice that when I change the ratio, the points on the domain change. The spacing increases by 5%, or a factor of 1.05 from the left side for each grid point. They are more closely spaced on the left side of the domain because it is usually good practice to have a denser grid close to moving boundaries where the composition profiles are expected to vary a lot during the simulation. Set the phase to FCC-A1, which was the other phase we saw on the phase diagram. Regions are always separated by phase interfaces, and the phase must always be different for each region. Click Edit next to Composition Profiles. Enter 0.15 in both fields. This is the material composition, and entering it here means that carbon will go from 0.15 mass percent on the lower left-hand side of the system to 0.15 mass percent on the upper right-hand side of the system, which we will see in the plot after we run the simulation. Click Apply. Finally, we need to define the thermal profile. This is an isothermal simulation, so leave that selected. Set the temperature to 1050 Kelvin. Notice that the Perform Tree button is grayed out and we are not able to press it. This is because the diffusion module is designed so that you cannot perform a calculation that is not fully set up. If you hover your mouse over the button, a tooltip will appear listing everything that is missing. We can see that we still need to set the simulation time, so set it to 30 hours. Now click on the Plot Renderer node. Change the x-axis variable to time, hours, and change the y-axis variable to position of interface. Change the unit to micrometers, but leave the default interface. Now click Perform at the bottom center of the program. Once the simulation is finished running, a plot will appear in the results pane. The plot shows the ferrite-austenite phase interface position as a function of time. The plot has the parabolic appearance that is characteristic for many types of diffusion problems. We can see that the curve does not flatten out, which tells us that ferrite has not reached equilibrium at this time. If we go back to the diffusion calculator and increase the time to 300 hours, then click Perform Tree again, we can see that BCC reaches equilibrium when the curve flattens out. Next, we will add a second plot to look at different variables. Right-click on the Diffusion Calculator node, highlight Create New Successor, and select Plot Renderer. Right-click on the new plot renderer and select Rename so that we do not confuse the two plots. Name the node Composition Profile C for carbon, then press Enter. Set the x-axis to distance, micrometers, all regions. Uncheck the box next to Automatic Scaling and set the lower limit to 0, the upper limit to 2000, and the steps to 200. Set the y-axis to composition, carbon, mass %. Change the time unit to hours, then place your cursor before the 300 in the time field. Add 0, space, 1e to the -4, space. This will plot the simulation for all 3 of these times. Right-click on the Composition Profile Carbon Plot Renderer node and select Perform Now. A second plot will appear in the results pane, which shows the mass % of carbon over a distance from 0 to 2,000 micrometers at the 3 times we set: 0, 0.36 seconds, and 1,080,000 seconds. Now I will show you a second way to set up the same simulation. Right-click on the Diffusion Calculator and select Clone. We now have a second diffusion calculator that has the same configuration as the first. Select the Ferrite tab and delete the region by clicking the red minus sign next to Region. This leaves us with only one region, austenite. Select Show Left Interface Boundary and select the BCC-A2 phase. Leave the driving force as it is. This means that the simulation will start with austenite only, which is the phase FCC. Then ferrite, which is the phase BCC, will form when the driving force for this phase exceeds 1e to the -5. Right-click on the Diffusion Calculator 2 node, highlight Create New Successor, and select Plot Renderer. Set the x-axis to time, hours. Select the y-axis drop-down menu and notice that there are not that many options. For instance, position of interface is missing. This is because the region is not yet created. In the first method, we entered both regions, but in this method, we only enter one region and ask the simulation to create the second region once it becomes stable. In order to get additional plot options, we must perform the simulation. So right-click on the Plot Renderer 3 node and select Perform Now. Once the simulation is finished running, we can select Position of Interface from the Y-axis drop-down menu. Change the units to micrometers. Our interface has also appeared. When a region with a phase is created during simulation, such as BCC in this example, an R is put in front of the phase name in order to give the new region a name. Click Perform again. We now have the same plot we made in the first example. Finally, I will show you how to run a non-isothermal simulation in the same setup. This means that the temperature will change. If we look at the phase diagram we created, we can see that at 0.15 mass % carbon, only one phase is present above about 1130 Kelvin, FCC. As cooling occurs, the BCC phase will appear once the temperature falls below approximately 1130 Kelvin. Notice that if we have a thin ferrite layer present at the start of the simulation, then it would dissipate if we were above this temperature. Therefore, we want to run a non-isothermal simulation that starts with a single region, austenite, and adds ferrite once it is stable. Right-click on the Diffusion Calculator 2 node and select Clone Tree. This gives us an identical diffusion calculator and plot node. Select the Diffusion Calculator 3 node and select Show Left Interface Boundary just to remind ourselves that BCC will be introduced once it is stable. Under Thermal Profile, select Non-Isothermal, then select Edit Thermal Profile. Set the initial time to 0 and the temperature to 1200. Set the second time to 0.3 hours and the temperature to 1050 Kelvin. The final temperature, 1050 Kelvin, is maintained during the entire simulation, which is 300 hours in this example, but it is only shown for 0.3 hours. To get a visual of the entire thermal profile, we will enter a time of 300 hours and a temperature of 1050 Kelvin. Then click OK. Select the Plot Renderer 4 node and select the menu next to Interface. There are no options because the region has not yet been created. Click Perform to run the simulation. Once the simulation is complete, a plot will appear in the results pane, which is similar to the 2 isothermal versions we created. The interface is now also listed because it was created during the simulation. We hope you enjoy using the graphical mode version of the Diffusion Module, DICTRA. You can watch additional videos about the Diffusion Module or other types of calculations by clicking the links currently on your screen.